in Finland. And let's get started then. Okay, so the background for this PEHKO project, I've been talking earlier on about the PEHKO results already a couple of times in ROADEX webinar a few years ago, but I'll have just a short summary. Those who have not participated them and are not aware about the history of PEHKO, so just in the beginning of few slides about that. So the PEHKO was initially, the reason why PEHKO was started was that after this new millennium started, so the government, due to the economical issues, so especially funding for new payments on our road network was cut down, and at that time the decision was made that the main highways, main roads should be kept in good shape. And as you can see on the left photo, so that mean that the paving mount on aerial road and especially on connecting roads, what we call low volume roads, also mainly were cut dramatically cut down. And what happened was that these cuttings could started to be seen after 2011, when the poor quality, amount of poor quality paved roads started to dramatically increase. Main roads stayed roughly on the same level compared with the value of 2000, but other roads started to deteriorate. And at the same time, in 2014, the total weights of the trucks increased from 60 ton to 76 ton. So and that was the other reason. So basically, the funding level in 2014 was we had about 60,000 kilometers of public paved roads when we calculate them as a two-lane roads. And the funding level at that time was about 130 to 140 million euro per year. And if we are doing a very simplified calculation, and that means that our annual funding was about, for the paving works, was about €2.25 per meter per year. So after if the annual costs are higher, then we are having a paving backlog, and if we are lower, then there are also money for other issues. At the same time, we had already ROADEX running for more than 10 years, and with the results and this research works, we published in ROADEX a report about what type of potential savings could be achieved if we are starting to change our practices and policies slightly. And in the ROADEX, we listed 4 issues. One is better drainage maintenance, then targeted rehabilitation, very precise location of rehabilitated sections, road-friendly trucks, and especially CTI values. Still, they are very good on low-volume road. And finally, fourth issue was road condition monitoring and proactive maintenance. And they, compared with the calculations and experience, the amount of potential savings depending on the road class and etc. can be seen in below. And then in 2014, the government and Finnish road administration made a decision that let's get started to pilot this ROADEX ideas and about proactive maintenance and we started this PEHKO pilot areas, and that was started in northern Finland in Rovaniemi and Kemi maintenance areas, in central Finland in Karstula maintenance areas, and then once we started to get immediately very promising results, that was also expanded. After that was expanded in 2018 to Hyvinkää maintenance area, which is very close to Helsinki. An ambitious goal was that this paved road network should be, after 10 years, should be in the better shape, and annual paving cost should be up to 50% lower than this what we calculated was in 2015 level. So what we started to do, first of all, of course, you cannot do predictions and calculation or modeling anything if you don't have data. So we started to do very extensive data collection, and this data collection was made by Road Doctor Survey Van, which has a GPR, LiDARs, and so it measures the surface shape, rutting, roughness, but also structural issue, ditch depths also, and such things. And this was repeated every year, every lane in all these three road networks. And then in the year 1, 5, and 10, we repeated also the traffic speed deflectometer survey from this Greenwood TSD system that and our contractor on this surveys has been coming from Poland. And then we've been analyzing huge amount of data has been collected over this 10 years and terabytes of data, and it has been analyzed different way and visually showing issues like for instance finding that the dynamic loading effect, for instance in this point cloud movie from Kemi-Tornio motorway, shows that once you have a bump and the suspension of trucks hits down, so it causes deformation in the pavement, and then it hits up, so it loses, and then it hits down again, and third, and experience was that 120 to 160 meter after used get these deformations in the pavement after one single pump, showing the big effect on the asphalt, and below that is statistic data of IRI and pavement strain classes, showing exactly the same issue, that the higher the smoother the road is, the lower in general we have the lower IRI value. So increasing roughness is increasing strains because of this dynamic loading. Then on structural side, on the top hand right hand side, very clear indication about pavement thickness and rutting. So deformations on deformations is annual rut increase millimeters per year. This is from central Finland, and on the right hand side low level is BCI calculated from TSD data and annual rut increase, again showing that once BCI up to 60, you are not having a major issue, but after 60 or 70, especially 70, then your annual rut increase starts increase, especially on the roads built on the soft subgrade. We tested also quite much different type of analytics methods, and we came up to to um, uh, uh, four type of analytics. Yeah. First of all, descriptive analysis, which is very much on online analytical using data visualization and reporting, and they are like used in traditional asset management systems. But then we developed quite much on diagnostics, diagnosis, and especially on using our ROADEX software to develop that where we could find out what is the reason for the problems, why something happens. Then third one, analytics, what we developed in PEHKO is predictive, which means that we can calculate what's happens in the future, uh, and on that is developing some algorithms to doing especially regression analysis, and for predicting the future behavior of the. And finally, the last one is prescriptive analysis, what we are very much using on and working on budget type of calculation and seeing the future. And prescriptive analysis is like AI is, for instance, in the future is will have a major role in this prescriptive analysis. Then let me see. Then couple of example of this descriptive analysis is example, and what we found really interesting and promising results was that we didn't monitor only the road surface, but our LiDAR system measured every year about 20 meters both sides of the roads, which means that we could manage the whole road section and measure also the slopes, inner and outer slopes, and ditch bottom levels. And in addition to that, we tested this MDI method that we've developed to New Zealand, measuring moisture content under the road structure. And in this point cloud in the right hand photo, we could demonstrate how this. So there it shows, this red one shows the anomalous moisture content under the pavement structure, and then the point cloud and this rutting looking shows the deformations in the and rutting and deformations in the pavement. And this is a nice example how it demonstrates that once you have an unstable outer slope that flows to the ditch bottom and filling the ditches and blocking the water flow in the ditches, side ditches, so that leads that water is flowing under the pavement structure, and once water is under the pavement structure, it's caused deformations. On the left hand side, it is just a statistics about again IRI and RAT and how deep are the ditch depth. And that confirmed, this is from the Finnish Lapland, and confirms that once our ditches are starting to be higher than 1.1 meter from the pavement surface, then we start to be on a safe level, related on the drainage side. One issue, of course, was how to find where are the expensive sections, and on our three test areas. And what we did over there, we calculated the distribution of annual RAT increase in each AADT classes, and and then we analyzed that, okay, where are the highest, or what is the limit for the, let's say, worst 20% or worst 10%. And we calculated also the cost, what is the cost for them, and found out that this 10 to 20% takes actually about 50% of our payment money. So we started to focus, first of all, locating where they are, and of course, this is from the Hyvinkää area close to Helsinki, and of course you can see major highways over there, but then you see a lot of black dots, orange areas also on lower volume roads that were increasing this annual paving cost. And then we started to analyze that in each area, that what are the features that explain them, why they are, what is the problem with them. We ended up 7 major reasons behind the paving backlog. And first 3 of them were related on the payment design, payment quality. Heavy trucks and weeks upgrade, like I told you, already showed this BCI correlation. Then heavy trucks and thin payments. Our payments are much too thin. If knowing how heavy our trucks are in Finland. Also, the third one is the payment quality. In some areas, there are like certain issues like aggregate quality, creep issues, paving type, etc. Then the next 3 are related to the daily maintenance, which is private access road junctions, and their drainage system, surprisingly big impact, about 8 to 10% in each areas. Side ditches impact was 4 to 5%, even later on we find that even bigger impact. And then winter drainage problem, and especially delayed removal of snow walls. And over there impact can be even 100%, as you see later. And finally, one interesting issue was also extensive use of de-icing salt on road sections with the thin pavements, and that was also causing issues. Then we later on we find out basically is that one on asset management or payment management, what we could call 8th problem is that we don't have enough funding for the payment maintenance, and then we have 2 reactive maintenance policies. So we are just moving more and more towards payment policies. So based on that and based on the allocation, we didn't get too much money on extra money. We get the small money for the research and data collection and for the extra first years to get things started. But after that, in the 10-year lifetime span, the money allocated for these areas were roughly the same that everybody else got. And each year we've been calculated the amount of annual cost compared with the first year cost. And actually first year cost is 2015 and to 16. And actually what we should have done is that we should have calculated the cost already 2014 and 2015, because that was in 2015 we already did rehabilitation work. So basically the real savings are even higher than what we can see here. But one issue what can be seen in this, that the annual changes based on what type of winter there were and what was funding, it was increasing a lot. And in only 1 year in central Finland was that the annual costs were even higher than original cost. And that was a really bad winter time. But in the lower hand, in this table, you can see that at the moment last year we were in Lapland and central Finland on the level of 20% as an average the whole time, or lower values. But in the maximum in Finland, we were 44%, and in central Finland, 36% lower than first level. So there were a lot of variations. And another issue was that so far we have been able to work and implement these findings mainly only on the main roads. And when once main roads are better built, so the impact is not so high. So anyway, the results were so encouraging that now there was a couple of years ago already was decision that we have to start to implement this also to other areas. And knowing the experience from other countries is that this is so a disruptive change, that this is not only the technology. We have to have a like a, like a, balanced transition to this proactive road asset management, and knowing that it's not only the contents or technology. We have to have changes also on the processes of our maintenance management, and the most important thing is the changes in the people's mindsets. And this people mindset doesn't mean only for the government people who are working on the road administrations, but also it covers the decision makers, contractors, consultants, everybody who is working. They have to understand why we are doing slightly different way. So based on these changes, we started last year to write a report about implementing these PEHKO results. Mainly the work has been done by myself and Vesa Männistö from FTIA, Väylävirasto, and the title of this report, it has been just been published, is implementing PEHKO results in paved road maintenance. And here are the main titles. First of all, why we are doing this, also telling about fatigue and distress mechanism and what type of information we need for structural and functional conditions. Then what type of network level analysis and programming should be done, diagnostics and design, guidelines, project level implementation, what is required for the daily maintenance, and then how we start, what are the next steps when we started to implement proactive maintenance. First of all, proactive maintenance, how we are summarizing that. Some like rules or guidelines. First of all, repairs are avoided if nothing is wrong. So just for security, we shouldn't be paved, because that was one issue that it was very much thought that okay, once the paver is here or there, we should pave all the other roads on this area. But if you are having a shortage of money, it doesn't make economically sense at all. Then the other issue is that if you have a damage in the road, so it never should become acceptable normal. So damage is always a failure, something went wrong, and you have to find out what or why it went wrong and react on that. So basically root cause of this damage has to be defined always before selecting maintenance or repair method. And then the fourth issue is this real proactive is that we have to monitor, find the system that we can react before the damage in the pavement. Like the basic issue that visual pavement distress, if we see in the pavement, it means that you are too late. And if we are doing then that, we get much longer pavement lifetime. We have smoother roads, healthier roads also for drivers, human body vibrations that we will talk later on in this year about that on the ROADEX. We have a lower CO2 emissions, and we have a major savings, which means that we can do more with the less. Then one issue what we started is that we are using the same terminology. And one was rutting classification, rutting mode definition. And now we are, and that has been actually used already quite a long time in Finland and accepted. So we are talking about this rutting mode depending, which explain what is the weakest part in the road and why you have a. And in addition to our rutting mode, of course, we have to have this linear elastic pavement fatigue, which is also one type of problems. Then showing one very important issue is showing that why we should go to these thicker pavements. So showing that the annual rut growth, if you have like a main roads in central Finland where the traffic volume is roughly same, so very clear correlation with the medians and 90%, 95%. But also IRI. For instance, the right photo is from IRI distributions on and pavement thickness classes, and especially when you start to go from 101 up to 150 millimeter, your roads, it's a major increase in also in the smoother, because thicker pavements, for instance, when you have thicker pavement, they you don't have to have so good drainage system, so they are more like a tolerate. Big roads with the thicker pavements is they are not so sensitive on the drainage deficiencies. Anyway, one new system was also and quite like a dramatic new news was that our rutting is actually not always increasing. It's a general idea that once you are having a road, so rutting is increasing all the years. But the very first we thought that this was like we problem with our measurement technology, but after verification we found out that especially on thin pavement, actually many years rut depths are not increased, but they are decreased, and reason for that is a rebound effect, and which means that because trucks are not driving exactly on the same lane, so once the deviation of where the trucks are driving and varying like human drivers are, its deviation is 30 centimeter, so it's actually bouncing back in the pavement. And this has been done quite much research on autonomous vehicles, but together with the Tampere University, where we verified this it is a very nice case on this, where we drive first in the morning one line, and then in the evening afternoon other line. So in the morning we were driving the red line, and after each passes we had an increasing rut depth. Then we had a coffee break where you could see even already rebound. But once we were starting to drive the green line in the afternoon, we came back to this original 0.5 millimeter level. And we did this testing in several sections in Finland, found out that up to 150 millimeter, even with the pavement about 120 millimeter, you could see this rebound. And that is one reason why we are now like recommending, especially when we have like having steering assistant systems and others, so we have to react that now when we still can. And knowing also how thin our pavement is, the grain here are the pavement thicknesses, and basically only close to Helsinki area on the left hand, PEHKO Uusimaa area, you can have a relatively thick pavements. But in central Finland and Lapland, the amount of payments more than 150 millimeters is roughly only 50%. And once you go to the lower volume road, it's even less. So, but the recommendation is now that always when we are doing paving work, so we should systematically start to increase pavement thickness. Then about rutting, which is the main criteria. We tested also IRI development, but you cannot calculate too well the annual life cycle cost based on IRI improvement, but because always deep ruts are the main criteria for repaving. So they are absolutely the best like variable to measure. But on rutting, the issue was very much that because rutting is a function of traffic volume. So we started to calculate in addition to the annual rut increase, we started to calculate rut growth per 100,000 vehicle. So rut per 100 AADT. And that was an interesting issue. For instance, study tires, we got a pretty good idea that roughly 0.045 millimeters per 100,000 vehicle. That's could be related on rutting mode 3, which is caused by where to do the studied tires. And everything else is our rutting modes related to 0 to 2. Compaction mode 1 rutting surface part of mode 2 in the subgrade limit. And here you can see what you can see here is that if you are, this is on the x-axis, there's a traffic volume. What you can see that especially roughly 6,000 AADT, the worst 20 and 10%, the rutting starts to increase. So the problems are not so on the highest volume. They are always pretty well built, but the problem starts to be around 6,000 AADT, and especially less than 5,000, around 4,000 AADT. It's dramatically start to be and these expensive sections, even though what you can see that there are also good sections. So we ended up to a recommendation now that in addition to make a limit guidelines now in the beginning, that what are the first target areas with the different, and we ended up to a lifetime category seen in over there. So roads less than 500 AADT lifetime calculate limit was 40 years, 500 to 2,000 30 years, 2,000 to 5,000 18 years, more than 5,000 11 years, and more than 10,000 is 8 years. So and that should be, and then we were looking that, okay, where are the each area, where are the sections that are higher than. And here is an example from Helsinki area. These red sections are not the ones who are not meeting the criteria. On the right hand side you can see also a map about RAT increase per 100,000 vehicles. So basically this is also a very good way to compare, because you can compare every road. Basically every road is on the same line. And in that way you can see and even low volume road, you can separate the worst low volume road with the pretty well functioning low volume roads. So this is what we are in a way starting. The red ones in Helsinki area are those ones that are the expensive ones, where we can really get savings on when we are starting to do a rehabilitation and strengthening over there. Then we calculated how much we have these roads and that are acceptable based on these limits. And on the left and first year and the last year is here. And what you can see in the left hand side, in Lapland we have been getting quite good improvements on AADT 5,000 to 10,000, but above 10,000 slight increase. But on the other hand, we don't have too much, and it was already 90% good acceptance level, so pretty good score on that. But what happened that less than 2,000 in Lapland, there's hardly any improvements or even going worse. On the other hand, in central Finland, we have been able to improve also the low volume roads. And only issues on central Finland is 5 to 10,000 people. But the most dramatic change is in Helsinki area, Uusimaa area, where we have got a really big improvements on high volume roads. So starting from 2,000, 5,000 and 10,000. In 2018 we were on the level of 30% meeting the criteria. Now we are around 60%. So very good development. But on the other hand, in Uusimaa also, we haven't been able to improve these low volume roads at all. Then one issue is this proactive policy is critical issue is this, that how we can detect this phase of microcracking where you don't see, because in microcracking phase you are starting to see some anomalous RAT increase, but the payment is still quite strong and it hasn't lost its tensile strength. So how can we find that? And according to our calculation, that with the Finnish payments standard payment structure, if you are repaving your road during the microcracking phase, for instance 50 millimeter or 45 millimeter new asphalt, you get compared that you are paving after you see cracks, you get 7 times longer payment lifetime. So you are going from up to more than 20 million axles compared with only 4 million axles over there. And if you calculated annual paving cost for your investment, so it's 60% lower. So our message is very much stronger, that what we can see in many of our roads, that you had a cracking and you just put a new overlay. So after 2 or 3 years, the roads look like that. doesn't make sense at all. And as I said, that monitoring payment distresses means that you are monitoring how late you are. But anyway, the question is that how do you know where you have a critical? And one issue is what we found out, that we calculated the strains, asphalt strains, using the Swedish equation on the deflection and pavement thicknesses. And what we found out that the critical strain value is that if your strain starts to go higher than 300 to 400 is the area where you don't see yet cracks. In 400 you start to see already patching, because you start to have a like a permanent strain over there, but you don't see cracks. So that's like a last time with our payment mixture design. If you go more than 400 up to 500, you will always see cracks. So strain calculation and strain-based system based on the TSD data seems to be very encouraging. The other issue that we have been using is and are now recommending is a microcracking analyzed based on the GPR, ground penetrating radar data, where we can calculate also that. And here's just example of our test and calculations, how this RD fatigue parameter is increasing as a function of roads. So this is a mean values and deviations that are increasing. So very nice correlation, and very interesting issue was that in 2017, after the measurement were like repaved, so you start to see exactly the fatigue on the same sections. And we've been monitoring these areas. So basically class 6 in this parameters, fatigue parameter, is that you see visual cracks. Class 1, if you see light blue, it means that it acts like a new payment. You don't see any micro cracking, and we can able to monitor them. And here's just example 2018, 2021, and then finally 2023. Calculating also the parameters, and what is really alarming and quite scary results, especially in the Helsinki area, that these indexes seems to be class like a class 4, 5, and even class 6 indexes are increasing every year since 2018. So even though our roads are like rutting is pretty good, but our fatigue in the asphalt surface, the fatigue sections with the problems with the fatigue and micro cracking in the surface are increasing. Then also on the payment distresses, what on the classification we have been introducing based on the ROADEX recommendations two new payment distress types. First one is top-down cracking, and which is related to the can be related to rigid remix payment on the top, and on the other hand, if it's too much like a super single tires, the other region. But then the other very important classification is for the diagnostics is what we call mode 2 cracking, which means that it's located in longitudinal crack in the center of the line, very often very straight strains, and that can be related to the soft subgrade and mode 2 rutting, and that is one thing. Also, on the payment distress classification, the problem is that we have a number of different payment distresses, and we are just calculating them together, but we are not classifying them. What is the reason for that? So what we are now recommending that you have to have a new payment distress classification, which is first of all load related distresses, number two frost action related distress, three is paving work quality related distresses, then other payment surface related distresses, which is raveling and pothole, very much related to the poor daily maintenance also. Then distresses in road shoulders, which are not so critical. And finally, transverse cracks. And once we have been doing them and classifying this way, it has been much more helpful and easier to compare before and after certain paving work, what has happened. And here in the right hand, you can see the number of this kind of classifications, and then on right hand side what happened after the paving work, and the topper graph shows that we have had a lot of big problem with the load related distresses and also edge cracking and finally transverse cracking, and this was like um, we know that we had a problems with the remix payment. Then finally making on the programming and design, where should we do if you want to go to the proactive maintenance, you cannot immediately change because you have always some reactive measures. So, but how to make the changes? And we made this kind of risk classification from zero, no risks needed on coming years. Major rule is that okay, next 10 years you don't need to do anything, and then classes 1 to 5, and on these classes there are like one is immediate reactive measures, and they are needed in first 2 years. Number two is immediate proactive measures. So, which means that the road is now okay, but if you don't do anything, you will have a major problem with the cracking in 2 or 3 years. So you should do something now. Otherwise it will be a very expensive section in the future. And then number 5 is extremely weak and uneven road sections. And once we start to move towards this proactive measures, so number 5 is very much like a maintenance focus on the worst sections, and we'll wait until we find more money and start to do a few sections, precise design on these sections. One issue also, that how do you know where do you have to do a strengthening design, or where do you need also only like from beginning to the end only one option, so one paving type. And what in over there we are using payment section homogeneity classification. And here's an example of also what is very expensive issue in Finland, and I would say other ROADEX countries also, that our payment sections are inhomogeneous. And here's an example of routing maps. In the top is 2016, and at that time, even these worst sections, you see more than 20 millimeter rutting, which means that you have to fix them. But as an average, in the mean, the rutting was only 8 to 10 millimeter on other section, which means that okay, it has had still about half of the lifetime available. And then 2017 after the paving, but now in 2020, for instance, in these sections, on this bad section, it was a 60 millimeter again, only 3 years after the paving. Once in this good section is 6 millimeter. So in 2016, the ratio from the worst to medium is about 2, and in 2020 the ratio is even increasing. It's almost 3. And we know from the asset management, economical asset management, that the road is homogeneous. It is what we call in asset management 70% rule or 1.3 factor. We decided to use this 1.3 factor, which means that 500 meter sections, if the 90% ratio in rut depth divided by median rut depth, if it's less than 1.3, this road is enough homogeneous. If it's higher, you should do some rehabilitation work, strengthening works on this worst section. And here is statistic. Here's a map from Helsinki area, where we have in Helsinki area we have about 45% meeting this criteria, but then in central Finland it's 40%, and in Lapland only 25%. All the others need a special design. So the inhomogeneity is a major issue and extremely expensive problem in our works that we need to get started if we want to be more effective and on our payment management. Then we have done some special recommendations. They are listed. I just show one issue is a traffic safety issue, which is also ROADEX related recommendation, which is quick changes in payment cross-roll, what is causing this warping risk. This is a special truck safety issue. And of course, it's loading related issue, because once in the inner curves, once trucks are warping to the right-hand side, it is causing heavy deformation in the road, as you can see in this red circles. And we are now recommending the limit that immediately RBS CSV values of at least 1% should be repaired immediately. Later on, we can go lower values. The other recommendation, what we have been finding extremely good, is steel grid structures on the roads that are resting on peat. We have done quite much research on them, and these structures are working extremely well. But if BCI, on the other hand, latest finding, if BCI values are higher than 120 micron, then it's not only steel grid, we need to have something else also. Daily maintenance, quickly at the end, daily maintenance is promoting side ditches. Side ditch depths have to be ensured that they are deep enough, and it's 20 to 30 centimeter lower than pavement structure bottom. All the life cycle cost analysis have been saying that it's absolutely the most profitable pavement maintenance measure that you can do. Payback time is only about 1 to 2 years, which is very dramatic improvement in the rutting rates if you are improving drainage. Also, access road culverts, verges, and pavement crossfall are over there. And finally, winter maintenance. Winter maintenance in 2019, 2020 in central Finland, where there was a very difficult winter and winter maintenance failed. We were too late, a little bit too late, and it was a very dramatic like you could see very dramatic impact in the deformation of the roads. Also, the latest finding is also that if it's a very cold winter, then we have to. But the most risky is this warm winters, and especially that if the snow shoulders start to melt and releasing water in the pavement structure, then you have lost the game. Finally, the implementation is that what is needed. We have been listening that that we have to understand that we have to go step by step towards proactive maintenance, but at the same time we have to know that there will be also reactive measures. But what is needed is at the moment we need to get started education, staff, consultants, contractors, main stakeholders. Like yesterday here in Rovaniemi was a meeting with the members of parliaments, forest industry people, and local decision makers promoting proactive maintenance. So this is the information need to be shared. Also, asset management policies, practices need to support proactive maintenance. And finally, we have to implement new technologies and start to implement also digitalization. So, which means that we have to have knowledge-based maintenance management. We have found out very good experience on that also on the gravel roads in central Finland. We've been testing that. That's another story. Daily maintenance always requires real-time situation picture. We have to find a system how to support better daily maintenance. And in the future, and because we need to have this real-time situation picture, is we have to develop at least partly crowdsourced data collection. Of course, systems like TSD or GPR, they are never in every vehicle, but roughness and other parameters you can monitor almost from every vehicle in the future. So this is just acknowledging and being aware that this is towards the future. And here's just some photos about PEHKO areas in taken last week, and so just showing that we have still challenges, especially on the older payment and getting fatigue and localized problems over there. So not this is not our policies is not solving all the problems, but at least we know that we are going towards right directions, and we know much better what are the main challenges with our paved road networks and what is the direction we should go. So with these words, thanks again. It was a 1 hour webinar, but anyway, thanks again. And I don't see any like that if there are